And so it's basically a set of ordinary differential equations whereby you say that the dynamics, so the growth essentially of the population of species I is multiplicative. So as in many population dynamics models, sorry. And so you have the first part, which is pretty standard. Mu I is going to be a growth rate. So that's just exponential growth. Then you add something which is called self-regulation. And so you can see with this term that essentially you've got something called a carrying capacity, which represents basically the maximum population that the environment can handle. So you can see that if SI goes above KI, these first two terms give a negative term. And so instead of having exponential growth, you have exponential decay. Okay, and so finally, and this is what really usually interests us, you've got an interaction term where you have alpha ij, which is an interaction matrix. And so if alpha ij is positive, this means that you're either competing for a resource, so species I and j, so the presence of species j is deleterious to the evolution of the population of I, or you could be that I is a prey, potentially, of a predator j. Okay, and conversely, if you have smaller than 0, basically this is like symbiosis, so both species are mutually beneficial, or it means that j is a prey of I. Okay, and so there's been very interesting stuff about the dynamics that have been found. So several regimes with, for example, chaotic dynamics. There's also several equilibrium that can be reached, etc. And so for this, I recommend you look at the work of, for example, Giulio Biroli, Félix Roy did his thesis on this, Guy Bunin. So there's many people that worked on this within the kind of community of spin glasses. But so essentially, we'll assume that there is an equilibrium to be reached. And so this means that we're looking for solutions satisfying the steady state. Okay, and so in this case, you can see quite easily by looking at the equation that really this amounts to solving a linear system. So you need to invert some matrix C. You still have your growth rates. And so here, Cij is basically going to be the first term, so relating to the self-regulation on the diagonal, and plus alpha ij, your interaction matrix. Okay, and so this is really the important bit. Whoops. This is really the important bit because, sorry, yeah.
Are there any criteria for alpha, for the alpha matrix for having?
Yeah, so definitely, because so what they've studied in the past is that you have a whole phase diagram basically depending on essentially. So alpha is usually taken to be a random matrix. In our case, it's not the case. We won't take that model. But if it is a random matrix, then you've got to be careful. Of course, if alpha ij, for example, is not symmetric, then you usually don't reach an equilibrium. Okay, so there's of course some conditions. I won't go too much into them, but so we assume here that the equilibrium does exist, but absolutely, yeah, you're completely right. And so here it's within the scope of what we're looking at because you can see that it's linear. And of course, you want SI to be greater to or equal to 0, so it's non-negative. And this is just from the fact that obviously you can't have a negative population in your ecosystem. Okay, so that's the first illustration. And so here we won't focus too much about details of the model, but it's just to give concrete example of what is a non-negative linear system. Okay, and so the second part is going to be portfolios. And so actually long-only portfolios, and I'll explain what this means in a minute. So basically here what we mean by a portfolio is really this vector, which is a size n, kw, where wi, so one entry of the vector, is the fraction of essentially wealth allocated to the assets. So this could be your stock, your bond, whatever, I. Okay, and we still have I then going from 1 all the way up to n, and usually assume large. Okay? And so here, we're going to make a bit of a leap, but we assume that return on investments, okay, so basically the amount of money that you're going to get from investing in I, are described, so of course they're going to be fluctuating by, so the expected return mu I, that's really your expectancy, and we assume they are correlated, so you have a correlation matrix Cij. So of course the statistics could be a lot more complicated, but really we're going to restrain ourselves to this. And so then the, say, what's called the Markowitz optimal portfolio is that which satisfies, sorry, basically, you know, the very kind of conventional optimization problem where you minimize some quantity. So here we take the portfolio variance, but I mean, hypothetically, you could have different quantities that you're trying to minimize, but really here it's basically the risk associated to the portfolio. And so it's basically the quadratic form of your covariance matrix with your weights. And you fix the constraints that your expected return, so what you want to get from the portfolio, is a certain value mu p. Okay? And so if you do this, it's actually a very, as I said, conventional problem. And so you can solve it quite easily. And it gives you that the weights are basically proportional to the expected return you want. And so you've got a part which is simply the inverse, once again, of the covariance matrix times the expected return uj. And then you have basically some normalizing factor at the denominator. Oops. Okay, so this is one possibility. And so that's how you solve the problem. And it was done by Markowitz in 1952. So when I refer to a Markowitz portfolio, it's really this, it's that satisfying this, this optimization problem, and so given by this formula. And so here, the thing is you can have two different options. You can have positive weights, which kind of makes sense. It's called a long position. And so basically the idea is you buy now, you sell later, and that means that you bet on an increase of the value of your underlying asset. Okay, so that's what you typically do. But the magic of financial markets means that you can actually sell things that you don't own. And so you call this a short position. In French, it's vente à découvert. So maybe that rings a bell to some of you. But essentially, without going into detail, you bet on the decrease of the asset at hand. Okay, and usually this is quite nice because you can insure yourself schematically against a decrease. Huh? J'ai fait quoi? No. Wait a second.
Sur Internet connection.
Yeah, I think
Looks good.
ouais.
Yeah.
Okay. Bear with me. Sorry.
C'est toujours sur Radio 1, ça.
Ouais.
It can sharp my connection.
Okay, we'll try like this, and so if it goes wrong again, let me know. So
I think it's important to ask a question.
Yeah, sure.
Does it change much if you try to maximize your output rather than trying to fix a value?
So if you try to maximize both,
Now, if you try to minimize the variance but maximize the view.
so basically what you'll find is that there's something called the efficient frontier. So you're always going to have a maximum return for a given level of risk. Okay, so schematically people kind of see it like this. So you can't get better than the best, and the best is this. So here you fix your mu piece if that's actually the best value that you can get. Okay, so you can bet on increase, bet on decrease. And so the thing is, sometimes you don't want to do this. So the problem with this is that it's riskier because you can lose a lot more than the value you had initially invested. And it's actually a hassle because you need to have some deposits. And also sometimes it's forbidden simply depending on the state of the market. So for example, as a bit of a trivia, at the beginning of the COVID crisis in Europe, usually short sales were forbidden on some indices. Okay, and so if it's forbidden, then you find yourself in the long only case that I mentioned earlier, meaning your weights have to be positive. And so here the problem becomes WI, whose sign is proportional, I mean, whose sign is given by the sign just of the numerator here. So if you go back to this expression, the covariance matrix is positive definite usually. So it's positive, mu p, of course, you want to have a positive return. So the sign is going to be fixed by the numerator. And so this means that you're looking at a problem like so. And so here, obviously, I'm happy because it's the same as before, right? So we're in the same case, it's linear because you're just inverting this linear system, and it's non-negative because you're banning shorts. Okay? Yeah.
Could you describe the dynamics? Because I'm not really sure. Like you start with a vector, and then after.
So here in principle, there's no dynamics. It's really like you solve the optimization problem one shot. Yeah. So you mean once the constraint is applied, or without the constraint in any case?
I mean, the vector you start with is like normalized to 1, and then.
So
I'm not really sure.
So here the returns, the expected returns are for fixed time set. So you say in a month, I expect this stock to be increased by so, okay. And so then there's no dynamics in the sense that, you know, you really solve the quadratic optimization problem and you have your solution, that's it. If the information changes, you might want to change your portfolio, but we're not considering the dynamics here. It's simply solving the optimization problem.
I mean, so is it like mu I is a number that multiplies or that adds to what you started with?
Okay. Now mu I is going to be basically the delta price, if you want. Very schematically, it's just going to be, so here.
It's not a percentage.
No, I mean, you know, it depends how you give it, but here in the spirit, it's an absolute return. Yeah, if I'm not mistaken. Yeah.
Joe, sorry, I didn't understand exactly your answer to this question. So if you minimize the variation of your of what you can earn, I mean, of your WI. So if you minimize sigma, is there a fixed expected an expected return?
So usually the sketch that you give is that, so for a given value of mu p, your solution, which minimizes the variance, is going to be given by the optimization problem at fixed mu p. And then the thing is, your variance is always going to increase as you increase mu p. So you can be as hungry as you want, you'll get more risk. And so the best you can do is here, is something called the efficient frontier. And so you can, these portfolios are impossible. And these are all those you can get. And the optimization problem allows you to get the best that you can. But so if you increase your return, you're mechanically going to increase your risk. Okay. All right. So now that we've introduced both examples, I'll kind of move on to the setup of the problem. And so as you can see, it's quite general. You need to invert a matrix. And so here, unfortunately, we can't be as general as we want. And you need to input some sort of matrix model to know, you know, in what regime you are and what you expect. Okay. So here we make the choice to take a very simple, but yet general model, which is to take a diagonal plus a rank 1 perturbation. And actually, the idea here is you say, okay, here we take rank 1, but potentially you can go higher. So it's kind of saying you've got an eigenvalue which dominates the problem, so you take this. So this is kind of, usually people either do this, or also you've got the whole random matrix theory side of things. But in our case, we think that's a bit more interesting to look at this, and I'll justify why for the two examples that we've given. But so here, the form is something on the diagonal plus, and so this vector beta is going to be basically constructing this rank 1 perturbation. Okay. And so we've got two interpretations for our cases. So for populations, it's clear, well, I mean, it's easy for me to say it's clear, but if you go back to the first expression, Zi is simply given by the growth rate over your carrying capacities. So this is specific for each species. And then this means that we take alpha ij, which is equal, sorry, to beta I, beta j. So we have an interaction matrix, which is in this form. And so this has a couple of consequences. The first is that we're obviously placing ourselves not in a predator-prey context, because you need opposite signs to have predators and prey. So here it's really competition for the resource. Okay, so you can imagine essentially similar species, for instance, some microorganisms that could be in competition for what the environment has to provide. Okay, and then beta I is essentially the dependency of species I on the resource. Okay, so in a sense, and so as a side note, we're going to expect this to be greater than 0, obviously, because if everyone has negative beta i's, it means that your growth is just everyone's mutually beneficial, which doesn't really make sense in this context. But so here, sorry, this is very badly written, dependency. So here, for example, beta I, if you're a very hungry species and there's another very hungry species, you're going to be competing harder. So beta I, beta j is going to be larger. If you're very frugal, you're better off. Okay. And so then in terms of portfolios, this is actually a very famous model. It's called single index or one factor risk model. And what we mean by this is that Zi then is going to be essentially the volatility. So it's called idiosyncratic volatility. So the volatility, sorry, associated to that stock. So specific to stock. So for example, from exogenous causes, so things outside of the market. And then you've got beta I, which is called the market exposure. And so what you're saying in this model is that most of the fluctuations come from basically amplifying or dampening the fluctuations of the market as a whole. So the market as in the average of all the products. Okay, so in that case, beta I greater than 1, so 1 is going to be the baseline. So you basically as volatile as the market. Beta greater than 1 is going to mean more volatile than market. And conversely, if your beta I is smaller than 1, then you're safer. Okay, so kind of the same spirit, dependency on the resource or vulnerability to the market. The lower, the safer in a sense. Okay, and once again, you expect this to be greater than 0 in most cases, unless you're completely negatively correlated to the market. So which is quite unlikely. All right, and so then the questions, I've been talking about these betas all the time. It's what's the distribution of the beta i's? So the distribution rho of beta, I'll note it. So right off the bat, we take beta i's to be identically distributed but independent. And so as I said, we have kind of a few, like we have kind of a shopping list, which is we need, an average value or typical value. So we're going to take it to be unimodal. Usually we'll take this value to be greater than 0. And so we'll also indicate, so it's going to be, unimodal. And we'll indicate that has a width, which we'll write sigma. So for now, I'm being quite, vague with it, but essentially you can use market data as a baseline because unfortunately you don't really have data on the species. It's quite rare to be able to do controlled experiments with large number of species. And so then on markets, you can have basically 3 cases, either Gaussian centered at 1, close to, and this is when you consider daily returns. Sometimes if you look at longer time scales, so for example, weekly, you'll have a bit more dispersion, something that looks a bit more like a Laplace distribution, still centered at 1. And so here this is 0. So there's actually very few values that are negative usually. And then what's interesting is also if you restrain yourself to a specific industry, for example, so industry specific, you get something that's usually closer to a uniform distribution. Okay, so it's basically families of distributions that are, in a sense, tightly bounded. Some sometimes have almost finite support or have support that's completely controlled. Okay, all right, so how am I doing on time? Not great. Then just as the last, not really assumptions, but really it's a setting that we put ourselves in. So for tractability, in this case, so in the paper that we did, we kept everything general, but here for tractability, I'll take Zi is equal to mu y is equal to 1 for all cases. So homogeneous, growth rates. I'll explain at the end how you adapt the solution to, but so for now, we'll just look at how the distribution of betas impacts really the properties of the solution. Okay?
In the case of population dynamics, do they have data about the beta distribution?
Unfortunately not. So we've actually looked, and even as for the matrix as a whole, there's not, that's why, you know, there's a whole Robert May, you take a random matrix and you say, just go for it. But really there's very little data, unfortunately. As far as I know. But yeah, we actually asked and didn't get anything. And so the final thing that we're looking at is WI. So now I'm just going to take the notation WI instead of SI. We're going either way. So we're really just inverting the matrix with Cij now with our unit rank plus diagonal model. And this is what we'll be basing ourselves on. Okay. All right. And so now for the interesting bit, or at least justifying the joke in the title, I need to introduce the spins that we've been talking about. Okay, because so far, so we have this problem, which as it looks is actually quite far from anything statistical physicsy. And so the good thing with this matrix model, obviously, is that you can invert it quite easily. So use something called the Sherman-Morrison formula. And so what you find is that now, still keeping WIs, everything can be written as a function of the draw, all the beta j's basically. And you've got this expression, okay? And so now the thing is, okay, we said that we're gonna forbid the negativity of these expressions. And so what do you do if you find yourself with a WI that's negative? Okay, so if WI is negative, you want to discard it. And if you discard it, the thing is you need to exclude it from these sums to recompute the WIs of the species or the assets that haven't been discarded. So this is why we introduce binary spins, which are not going to be -1, 1. They're going to be 0 or 1, obviously. And so if theta I is equal to 0, it means that you're excluding the species has basically gone extinct or the asset excluded from the portfolio. And if it's equal to 1, you're not touching it. And so then you can rewrite your actually now long only optimal portfolio or your final ecosystem with these spins, which allows you to satisfy the constraint. Okay, and so here, I'm sorry, so this is kind of how I understood your question earlier, but maybe that's not it at all. But so now you can actually think of a heuristic algorithm to construct it, as in you start with a portfolio, you look at the sign of the WIs, then if WI is negative, take theta I is equal to 0, and then you run again. So that's a heuristic part. But if you want, you can actually be exhaustive and consider all 2 to the n combinations of theta, of the vector theta, so all theta i's, and then you can try them all, keep only those that are satisfying the constraint, and then what you want to do is exclude as little as possible, so you'll keep the one that's most full, in a sense, okay? And so an important indicator for the state of our system is going to be something that we call the sparsity, which now that I think of it, should maybe be the opposite of sparsity actually, but so it's the level of fullness of your solution. And so I'll write it n, and here the average is taken in, so what I'll call from now on the disorder, which is basically the draw of beta, okay? And so it's basically the fraction of positions are occupied or species that have survived at the very end of the dynamics, okay? And so this obviously is more or equal to 1. And in a sense, this is really our order parameter here in terms of statistical physics lingo. De quoi? Ah, comme ça?
Voilà.
Ok,
So I think I missed a little bit the point where you introduced the spin. So since I guess it's important, it's in the title.
Yeah.
So you were excluding. So you pull your BTIs from your distribution. You include the WI, and then it's the WI negative. You want to exclude that. Okay.
Yeah.
But then what I didn't get is why you have your theta I that enter into the formula.
So you mean here?
Yes.
So the thing is, when you exclude it,
Yes.
really it means that you're restricting kind of the universe you're considering. So for species, you want the solution to be not impacted by those that have died out before. And so this is why from these sums, I mean, it's kind of a notation thing. You could just say J running inside, but it's really this indicator that is it still in? Yes, then it's contributing to the sum. Is it not? Then no, it shouldn't be contributing to the sum. And as a result, and then you recompute. Because there's also the thing that, and here I took implicitly, sorry, and I should have been more clear, but you have the sum of WIs, which is equal to 1. So really when you're excluding stuff, it completely reshuffles the solution for the rest. Okay, so in this sense, it's very interacting, and so the spins represent the interaction in that degree. Okay.
Question.
Yeah.
It's maybe a silly question. It's about this apparent frustration there. I mean, intuitively, the more diverse is your portfolio, the more robust and the better it is. Still, if you want to optimize and minimize the risk, you can find negative weights.
Yeah.
And isn't it contradictory with the fact that?
No, because so negative weights are going to be associated kind of in a 50-50 way, in a sense that therefore if the market, so if you're thinking about the portfolio case, if the market goes bad, if you have negative weights, well then these, you make money, right? So you're insuring yourself against loss. When you're long only, and this is why we'll see, I'll mention again in a minute, but here you can see that if beta I is big, then WI is negative, yeah? And so it really means if you're too risky, I can't insure against you by betting on the negative, so I need to just not look at you.
Okay.
Right?
Even if they were like a really good economic conjecture, for example, then I guess that would be like a really positive term in all your C matrix, and then there would not be negative weights anymore in your optimized portfolio.
Yeah, so it's I mean, in a sense, yes.
Okay.
So it's more going to be smaller betas. So if you have limited risk, your beta is going to be small, and then you're happy. You don't need to exclude anyone actually. And as you'll see, and so actually this is a good point because now we're going to study M as a function, well, basically of the distribution of betas, of its width in the case where you fix it, and also of N, because of course the size of the portfolio is going to be important. And you'll see that there's the whole regime where you actually don't exclude anyone because you don't need to. All right, so we'll do this right now. And so what we have here is that to solve the problem, and this is really, so of course there's a spins, but the spin glass-like approach is really from the self-consistent approach that we took. Because of course there's different ways to formulate the way you want to solve this, but going back to the formula that I showed here, what I mentioned is that clearly if beta I is too large, you'll basically remove it, because we've said beta J's are overwhelmingly positive. This is clearly positive. This is going to be mainly positive and actually very likely positive. And so the only way you can have a negative weight is if beta I is too large, which goes back to the intuitive thing that I said. If you're a species and you consume too much, you're more risky to just die out. Okay, and so because the large beta I are removed, we can actually reformulate the thing, I mean the whole problem, as a threshold. I'll write this beta tilde plus, so the tilde means the threshold is specific for a single joule of beta I's, okay, such that for all beta I which are greater than the threshold, beta I will be equal to 0. So you're discarding all the things that are too risky or too hungry to be included in the final portfolio or ecosystem. Okay, and if you use the formula above and you basically set it to 0, you have an expression for this threshold, which once again is going to be sample specific. And so now you have this expression. Whoops. Beta J, beta J. Okay, and so now what we want is to compute actually, so the fluctuations about the threshold will be important, as you'll see in a minute. But really what we want is to compute the expected value of this on the disorder once again. So for any draw of beta, because then what we have is that M, which was the level of fullness of the solution, can then be evaluated just by looking at the distribution of the betas. Because then if you have an average threshold, all you're interested in is what's the likelihood. So my sparsity is going to be the likelihood that a number of the beta i's that I've drawn are smaller than the average threshold, right? Especially in the limit n goes to infinity or n is very large. Yes? So then the question is, for a given value of beta, without any information about the rest of the system apart from the size of the system, so I give you a beta, I tell you you're part of a portfolio of size n, what is the probability of inclusion? Okay, so really we want a distribution of inclusion that only takes into account my own draw of beta and that averages out what happens for the other beta. So we write this function fn of beta, and so index n, because implicitly it's completely dependent on n, and it's going to be the probability that theta I is equal to 1 given that beta I is equal to beta. Okay, and so obviously we know a few things about this intuitively. We know that when beta is very, very small, it should be equal to 1, this probability. We know that on the opposite side, it should be equal to 0. And we know that the crossover between the two sides should happen around beta plus, the average value of beta delta. So at this stage, I can do a nice drawing what I expect this function to look like. Actually, I also want to know the way it's peaked. So looking at its derivative about the crossover, and so it's going to be a smooth step, conjecture, but of course it makes sense that it's monotonically decreasing at least. And so we're going to conjecture that its derivative is very peaked about beta plus, and it is so with a width which is going to decrease with n, and at this stage we don't really know at what rate. Okay, and so here the crossover happens beta plus, and you go from 0 to 1. Okay, and so this is going to be central for our study. Why? Because if we take a first assumption, which we can check at the very end, kind of with a cavity-like method, we suppose that theta I and theta j are uncorrelated, and bear with me, at order 1 over n. So they are obviously correlated to some degree, but we're going to conjecture, that it's smaller than 1 over n. And so if we do this, it means that we can apply the central limit theorem to the sums that we had. So these sums of a beta j squared, theta j, and beta j, theta j. And so this means now that we can write, for example, 1 over n sum over j of beta j to some power k. So it's going to be 1 or 2, theta j, and it's going to be approximately equal. And so bear with me with the notation. I'll explain what this double bracket means in just a second. But importantly, there's 1 over root n fluctuations. And so we have the average of the fluctuation which is equal to 0. Its variance is going to depend on k. So we'll have one expression for beta squared, one expression for beta. And what I meant by this double bracket is really the moment, but conditional to the fact of inclusion. So it's really the integral over the whole domain, but of beta to the k, the density of beta, okay, but then you want to include this fn of beta. So you want to, because of course this term is just the average of beta I theta I, right? So to compute this average, we use the function that we've just introduced. Okay, so now we're all set, because what we can do is, using this assumption that allows us to introduce central limit theorem, the ratio here, sorry.
Maybe just a question that maybe you can come back to later.
Yes.
Is it obvious that the distribution of beta will remain nice and that it doesn't exhibit, for example, a phase transition or like
so you mean
double peak and or something like this, or multiple?
So you mean the distribution of betas? that are included.
The fact that the beta threshold, if you scroll down,
Oh, scroll down.
yeah, the fact that the mean beta threshold is a good character, a good estimator, and which essentially means that you assume that the distribution of your beta plus over the sampling is nice. So it's not the distribution of beta, it's the distribution of the beta plus tilde.
I see, yeah. It's a good question. I think I'll touch upon it at the end when I talk about the idea that you can.
Just because I didn't want to forget the question, but we can discuss.
No, it's a good point, but I think it's related to what I'll talk at the end about the multiplicity of solutions in a sense, and the kind of. So, for example, if in the population dynamics you have some noise which could alter the way the evolution is not sequential, then I guess you have a good point. Like, it's not guaranteed that beta i's are going to be removed sequentially and in a nice way depending on the joule. But I guess if you do remove them, so if you actually have an expression which is this, and a nice enough distribution of beta and a large enough sample, I think it should be fine. But maybe you can discuss at the end. That's a good point. So now that we have these expressions here, we can go back to this ratio and basically develop everything at order 1/n. And so what you find is that beta tilde plus, and so here I won't write the whole expression because they're a bit nasty and they'll get nicer, but basically is going to be the average value that we're interested in. And so plus, because I use the CLT, 1/√n some noise. The noise is centered. And so I'll call this variance, which you can compute explicitly, well, explicitly in terms of these, say, conditional averages or moments. But so I'll write it just as gamma squared so far. And at this stage, just this simple expression is actually quite useful because it gives us a lot of information. I'll show why. So the thing is, if we go back to the definition of our step Fn of beta, it was the probability that theta I was equal to 1, given that beta I was equal to beta. Okay? But now if you think about it, with this threshold idea now, it's really the probability that beta, so beta I equals beta, so beta is smaller than the threshold for this specific draw. Yeah? And so if you remove beta plus on both sides here, whoops, you have beta minus beta plus, and smaller than beta tilde plus, well, minus beta plus, and we've just shown that this is basically Gaussian noise, okay? And so then you can show that this is the probability that your noise, which has variance gamma squared, is greater than now √n beta minus beta plus. And this is just 1/2 an error function. And so you have a √n. So this gives us two important information. The first is that it's symmetric, which was actually not necessarily true a priori. And then is that, remember earlier I called this the exponent alpha, so the way it decreased in n. And so we know that alpha is at least 1/2 because of the √n here. And so the question now is, how does gamma well, evolve with n? Because it's likely that it's actually also going to be decreasing with n. And so now we have to introduce a second assumption, which really comes from numerical simulations that we made quite early on, which is that you're in the scaling regime with, I mean, for the solution, what interests us is the scaling regime where sigma is some chi/n. So recall sigma was the width of the distribution of beta. Yeah. And so the reason why we have this is that when you do numerical simulations and you look at the evolution of the sparsity m, you found an immediate collapse in sigma n. So you think, okay, chi is the important variable, so we just rescale everything relative to this. Okay, and if you do so, and I won't show it here, but what's nice is that the magic happens, and now your variance for your noise, so the noise relative to the threshold, decays as 1/n. It also simplifies beta plus. And so if you bring everything together, you have that Fn of beta, you now know is some function h, which is complementary error functions and some constants. That goes as n of beta minus beta plus. So you know the scaling, okay? And I can write a very nice expression for beta plus. So I recall I didn't write the whole expression, but using this scaling regime, you have that beta plus, so the mean value that interests us is just this conditional average of beta squared, so the second moment with the condition, over beta plus 1 over n, the correction that's just 1 over beta, and then smaller order terms. Okay? And then there's a final trick that we introduce. And so for those of you, sorry. For those of you that studied maybe condensed matter physics, this is a trick that comes from, usually it's Fermi-Dirac distributions, and you want to, at high temperature or low temperature, have some expansions. And so the idea here is really to say, well, we have our function fn of beta again, and we know that basically when n goes to infinity, there's going to be a heaviside step, and then, of course, you have some corrections, and we know that the corrections are going to be at most 1 over n because we've shown that its peak is 1 over n. And so basically the idea, without going into too much detail, is that you write fn of beta is just this heavy side relative to the threshold plus some 1 over n correction, and then maybe you can go 1 over n squared, etc. And so the way you do this is simply take these truncated moments. So now you can compute, not truncated, sorry, but conditional. And so what you can do is do an integration by parts. So you introduce derivative, sorry, of fn, and everything works fine. And the very nice thing is that actually in our case, this term is equal to 0 because of symmetry. So because we've shown that the step function was symmetric, it actually turns out that you can remove this term completely. Okay, and so what we find at the very end is that you can rewrite these conditional averages just by considering the average threshold and then the distribution of beta, and then you have order 1 over n squared terms that we don't really care about because we did everything at order 1 over n. And so for convenience, I'll write these now truncated average, so with a cutoff as just beta k with a c for cutoff. Okay, and so finally, we have an expression which is beta plus is equal to basically the same thing as above, but with the cutoffs. And this is self-consistent in the sense that, of course, you've got beta plus on the left side, and then the bound of the integral is beta plus. So for some given distribution rho of beta, you should be able to solve for beta plus and then compute m. Okay, so this is really the heart of the calculation. I hope everything was relatively clear. And so, for example, if you take rho of beta, so the beta has to be Gaussian, and so centered at 1, but any positive average, any positive value, sorry, will be fine. We've got some variance sigma squared. We said sigma is chi over n. And so at this stage, all you need to do is you can introduce an ansatz that beta plus is going to be so 1. So it's going to be bigger than the average usually, but actually not necessarily, but it's going to be 1 plus chi over n, so basically 1 standard deviation. And then some function of chi, because that's what we've observed, sorry, numerically, is that everything depends on chi. And so if you do this, then for example, m, you can rewrite, given that it's the integral all the way up to the threshold beta plus of rho of beta is just, for example, and I won't write it all, was 1 plus, and then you've got an error function, and you can just replace f of chi and something like this. And very similarly, what's nice is that using just stupid integration by parts, you can rewrite all these cutoff moments as some functions of the usual functions related to the Gaussian distribution. And in the end, you have a nonlinear equation for f of x. So you solve for f given some value chi so that you fix. Okay, so for any chi, you need to do this numerically because it's a bit nasty, but if you do so, what you find, and so this is related to your earlier question, Paul, you find this. So here, sorry, function of m actually for a while it's going to be stuck at 1 because you're not excluding anyone. And then what you observe is some decay, and actually this you can present as a log scale. And the nice thing, so now I'm going to ask you to trust me because I'm not showing any figures, but we did numerical simulations and they match very well. It's perfect. The theory is great. Trust me, it's fine. No, but it does work. And so then you can actually do asymptotics analytically. And what you find is that m, when n is very large, so usually we place ourselves in sigma fixed to some value reasonable that you can actually check with data from Marcus, for example. You increase n, and what you find is that it's basically a log correction, but importantly, is basically 1 over n, which is a fast decrease in the sparsity. Okay, and that is for the Gaussian distribution. And so you can check the asymptote works fine as well. And what's interesting is that now, and then I promise I'll stop with calculations, but so if you take basically what's called the generalized normal distribution, so it's something that you can use to interpolate between usual functions. So it has a shape factor b, and all I want to say is that b equals 1 gives you a Laplace distribution, b equals 2 gives you Gaussian distribution, and what's interesting is that b goes to infinity gives you a uniform distribution. So it kind of covers the range of distributions that we were initially interested in. And what's really exciting is that something here happens which was not expected. It is that for any finite value of b, so when you're considering distributions that essentially have bounded support, because b that have an unbounded support, so because it's either Laplace Gaussian, something with thicker or smaller tails, but it basically goes as your correction, and it's basically dominated by 1 over n still. However, if you take b goes to infinity, you have a completely different decay in 1 over root n now, which is much, much slower. Okay, so that was kind of a surprise, this crossover between the two regimes. And it's interesting because at this stage, you kind of wonder if it's related to the size of the support, and the fact that strictly bounded support completely changes the decay. Okay, so just to summarize, and then I'll give you my last section. I'm not sure how stringent we are on time, but okay.
So a question about the fact that you said, so it's related to my previous one. When you have the self-consistent equation,
yeah.
So you always have, so there is no multiple solutions.
So
the beta plus equal exactly.
Yeah.
So if you plot the second part as a function of beta plus, I mean just for the Gaussian distribution, for instance, depending on the parameter, you never cross the diagonal.
Usually no, and I mean,
or you cross it once only.
So for me, I've only encountered cases where you had one solution, or at least one positive solution, which is really what you're interested in. To be completely honest, I didn't explore like necessarily, completely outlandish,
So there is something that makes. So essentially, I'm addressing the properties of this function of beta plus that is written there on the right.
So this one?
You have beta plus equals something, which is a function of beta plus.
Yeah.
And I'm asking about the asymptotic properties of this function. So when beta plus goes to infinity, when beta plus goes to 0 or to minus infinity, and then when beta plus is close to 0. And are there general statement that can be made? Because typically when you solve this kind of self-consistent equation, for example, for magnetism, you always get this tangent hyperbolic stuff.
Yeah.
And so by controlling the slope, you control the phase transition.
But
so are there strong statements that can be made that ensures the unicity of the solution, things like these things?
So I think the thing is that we directly place ourselves in the regime where you have this, right? So your solution is necessarily going to be of this form. Okay. And so this means that f of chi, so the only thing that you need to solve then directly is f of chi. And f of chi, you can know several things that, that basically based on, it's going to be a decreasing function. Okay. And so it can get very negative quite quickly. But so I think necessarily you can't have it too close to 0, because then, you know, you're really at the typical value of beta, right? So you're in the case where you're not actually excluding anyone. So f of chi is equal to 0 is really going to be your baseline. Okay. No, it's actually a good question. I didn't really think of it in that way, so I can't give you a very general statement as to how, but it's a good point. But from the observations that I've made in the regime of interest, I think that's probably the key word here.
Yeah.
There wasn't anything fancy going on, essentially. So the solution was easy to find, because also, so you know that you place yourself, you know that you
say what.
no, but don't worry, there's interesting stuff going after. No, so, and now, okay, I've shown you, okay, so we have this decreasing function n, and you might wonder, okay, but we don't really care, maybe. And so this is where I try to convince you that there are interesting implications despite the unicity of the solution, which is that, okay, so beta plus might be unique, but there is a multiplicity of solutions, and I'll explain how. So remember how very early on, I told you about, so if we go back to, you know, just this type of stuff, where I told you, well, if you want to compute m, you can have the heuristic approach where you just discard stuff as you go, and then once you have no negative solution, you stop. But I also told you can be exhaustive and just take any configuration of theta I. And the thing is, if you do this, you're actually going to find a lot of solutions that satisfy the constraints, but that are not optimal in the sense that you've basically made die out some species that didn't need to be, or you've excluded stocks that didn't need to be, right? So the thing is, now when I'm talking about solution, it's really a configuration of theta I, which satisfies the constraint, okay? And the thing is, this can be very large, and because actually m, our threshold, and then m was very related to n, you know, so the size of the portfolio you're considering, every time you're considering these suboptimal solutions, what you're really doing is reducing the universe, or you're effectively reducing n. So you're excluding species that don't need to be. So what this means is that really you're redoing the same problem, but on a restricted universe. Yeah. And so because this is so related to the sparsity that we've computed, we can actually write an equation. So I won't go into the detail because it's actually a bit, I mean, it's a bit long, but so you can write basically using cavity-like approach. So you add a spin, what happens, etc. You can write an equation for the average number of solutions that, using kind of probabilistic arguments as to m, which is really the probability of inclusion at this stage, is going to be strongly dependent. And so now, once again, like we had found two regimes for the sparsity depending on the distribution of beta, you find two regimes, which are that essentially you go as exponential of root n when you're in the case of finite b's. So recall that was Laplace, Gaussian, etc. distribution. So you'll have corrections, but essentially you're going like this. And for infinite beta, you're to the 2/3. So in both cases, I mean, the take home is that it's very big, right? And it grows very fast. And there's two important stuff to be said around this. And so for those of you that know spin glasses a bit, the interesting thing here is that actually log of ns, so the typical number of solutions, is not equal to the log of the average number of solutions. So there's something tricky going on. And unfortunately, so far, so in the work that we've done, we haven't actually computed the quenched proper average that would be more representative. But what's interesting to think about is that because the sparsity is so sharp in a sense, some fluctuations relating to the specific distribution of beta that you're considering can give you many more or many less solutions. And this is why you have this typical is not equal to average type of thing going on. Okay. And the other interesting bit is that if you introduce some measure of energy, and so in the optimal portfolio case, it's obvious that, you know, the goodness of your solution is going to depend on the variance of the portfolio. So if you look at some energy, and so for example, the portfolio volatility, but actually for species when they've been studied in a kind of thermodynamic approach, there's always some Hamiltonian as well that's defined. So if you compute this, you actually find it's very similar for many of these solutions that may have a small overlap. So what I mean by this is that I'll draw a little sketch, which I hope won't be counterintuitive. But if you imagine your solution vector and actually your beta vector is ordered in terms of beta. Okay, so the higher is at the top. So of course you're going to have your threshold that we computed that we're happy with. Okay, and so I told you the best portfolio or the best ecosystem, or at least most diverse you can do, is basically this. You include everything below. However, because it's so size dependent, you can imagine that maybe, well, you can take this, exclude all those below, and you still have valid solution in the sense that it satisfies the constraint. Okay, and the thing is, with the drawing that I made, this one's going to be horrible because you only have large betas, so the risk, for example, is going to be bad. So this is not one of the ones I'm talking about. But for example, you could imagine something which is marginally smaller. In this case, it might be very, very close. Or you could imagine something which is just offsetted by some, and which is still very, very close in terms of risk. Okay, so unfortunately, I didn't prepare the figures, but really then you can see this, and you have to study it numerically, but it's basically like a glassy landscape of energy, but for the quantity that you're optimizing. Okay, so the multiplicity of solutions also comes with this basically spin glass-like landscape, which is interesting. So for example, and this is something that you may have heard, for example, Jean-Philippe talking about, but how do people make choices if you've got marginal solutions that are very close in terms of quality? Okay, and the second part, which is very related to this, is something called disordered chaos, which has been seen in the past in spin glasses. So the question is, okay, you have something that's very sparse, so naturally the statistical overlap between two solutions is naturally small. Plus you have these many solutions that don't necessarily share the same assets. So what happens if you perturb the draw of betas for some given value of n? So for example, I take beta I minus 1, so if I'm centered at 1, and I transform it, and I take, for example, beta I minus 1, and then I multiply it by some epsilon times, I don't know, some white noise, normalize it in some way that makes sense to you. So usually in spin glasses, they do this. And so eta I is just 0 mean unit variance. And of course, epsilon is assumed to be small. And what you find, and once again, it is numerical, but if O here index n is some overlap between the two solutions that you found, so the most diverse solution that you're considering for the problem, well, then you can find the correct scaling for epsilon and sigma. But what you find is that if you're in log scale, it decreases like a parallel. Okay, so really what we mean is that the overlap O essentially goes to 0 for n is very large or very small epsilon. Yeah, so this is actually quite important when you think about it. It's quite exciting and also maybe a bit worrying. But so if you think of ecosystems, for example, you think, well, maybe you have a slight perturbation to the environment, or it's the way, you know, the species needs some resource, so maybe the resource itself is altered, and then you can find yourself with actually the previously optimal ecosystem that was living there is actually no longer as good as at all, and you can have, you know, really strong changes. And for portfolios, you can think about, well, depending on the way you measure your betas, which, you know, depends where you work or no, well, if you change it, or actually they're dynamic, they change in time, it's not stationary. So maybe do you want to have a very optimal portfolio that will be good for a week, or do you want something that's maybe a bit suboptimal but more robust that you can keep for a year? So these are the type of practical questions that come with it. And so with this, I think it's a good time to kind of sum up what we've talked about and what we found. So essentially, the constraint leads to sparse, also actually quite significantly distribution dependent, which is not usually the case for very large systems, solutions. This in terms brings us multiplicity of quasi-optimal. So in a sense, of course, the optimality can be debated, especially for species, solutions. And so these two things together mean disorder chaos, which practically is something that's quite interesting. And so just as a side note, because I said at the beginning, if you now consider heterogeneous mu-i's, for example, so growth rates or expected returns, the procedure is the same. I mean, it's very similar, except now you need to consider basically a threshold on the ratio beta over mu. So basically it means that if you have a very strong growth rate, for example, you could compensate for the fact that you're very hungry, and if you have a very poor expected return, even if you're low risk, you're not going to be included in the portfolio. Okay, so with that, thank you very much for your attention. I hope it was relatively clear, and of course, I'm happy to take questions.
Can you compute can you compute the average of some observable on the suboptimal set of solution? Let's say that you want to compute, I don't know, your return or something, but not for the optimal solution, which is, but
so
average over all the minima.
So I think this is actually initially what we tried to do, is if you want to do this, I believe that what you need to do is take the standard kind of spin glass approach, where you basically write, an integral over all the degrees of freedom, and then you write a heavy side, so all the configurations c to I, so actually a sum, but, and then you include your heavy side step function to ensure the positivity, and then your observable that you want. And so we tried to do this, but the thing is, very quickly in these cases, you restrict yourself to Gaussian betas, because you need to compute the integrals. And so initially, we actually tried to compute a number of solutions like this, and it was pretty tricky. So retrospectively, probably because of this, actually, because then got RSB and stuff like this. But hypothetically, I believe it should be doable, because really, if n is large enough, you do the standard thing, integral is the sum, then
because this could be somewhat the reassuring part with respect to what you were saying about disorder chaos. Is that if you assume that at the end of the day, the agents actually they don't find the best solution because it's too hard.
Yeah.
Unfortunately, they don't find it. And so on average over the agents, you are living on the suboptimal stuff, and this is robust.
Yeah.
With respect to a slight small epsilon.
It's true, yeah. No, that's a good point. The thing is that so the small epsilon is true for the best of the best, but it doesn't necessarily mean either that if you're not the best of the best anymore, you're horrible. You could still be, reasonably good. So I think, I think there's strong numerical evidence that what you're saying is definitely true. But yeah, no, it's true that I think the whole problem now, the next step would be if you want to compute quench stuff and get more representative averages, you need to go through this, which is quite a hassle. But yeah.
Nice.
Perhaps I have a question, but
yeah,
perhaps it's a silly question because you made somewhat strong assumption on the distribution of beta. Do we still observe this? I mean, how about the robustness of your results if we are looking at bigger tail distribution for beta? I don't know if it is relevant.
So right away, the thing is, if you have infinite support, there's something that happens if you look at, for example, heavier tail distributions, which is that if you increase, for example, the variance, you'll initially, so if you look at n, you'll initially have what we had, and then actually you're going to go back up. Because the reason for this is if you have thicker tails, yeah, here you're going to exclude a lot of solutions, but because you get negative solutions, you'll get negative beta, sorry, you'll re-include them. So actually what happens from my observation, so they're still unimodal, so they're well behaved, but if you take too thick of tails, then the probability that you're drawing some negative betas is, quite sizable. And then what happens is that the ones that you've excluded because they were too risky start to get compensated by the ones that actually, and these solutions allow you to compensate for these not solutions. These betas allow you to compensate for a lot of riskier stuff because you're essentially, so if you think of the portfolio, it's exactly like doing a short. You have something that's negatively correlated to the market and you can include it. So we didn't look at it too much because in a sense, it kind of trivializes the problem a bit. Like, because if you have a too wide distribution of beta, you'll just include it.
Okay,
Yeah.
If the tail is too thick,
Yeah.
you could have just a uniform.
Yeah. What could be interesting is something like, I think it's a beta distribution.
Yeah, one side,
which is
bigger
or
tail,
log
yeah.
normal. We actually started with log normal at the very beginning. It seemed like it was similar and probably a sharper. What I conjecture is that maybe it's stronger than 1/n decreasing n.
So you even with beta distribution, you still observe this S shape for M.
Yeah, it has to. It has to decrease at some stage. And what I'd expect is if you have a thicker right tail, you'll decrease faster because you're just excluding more and more. Yeah.
Yeah.
But I guess like if you go very exotic, you can find.
But I find this interesting because, I mean, I suppose the real life data are much more like the drawings you did, like.
Like this one?
I mean, this is not necessarily like very, very thick tail distributions.
It's actually the opposite. So usually there's more sharp cutoffs that naturally you'd expect there not to be. So for example, I can't really say much about the species because unfortunately I haven't seen it, but even then, like, it doesn't sound too likely that if you're really in this framework where you think either you compete or you're mutually beneficial, it doesn't sound incredibly likely that at some stage everyone's going to start helping each other. Like, you know what I mean? Like it's probably, I'd conjecture that there's a sharp stop at 0 basically, and that you're only going to be on the positive side. And for what's interesting is if you look at financial data, you can have thicker tails on the right, but never on the left usually. So there's also a bit of skewness. It's a good point though. I mean, the skewness, stuff like this that you need to consider. But I think it kind of joins the answer that I just gave, which is in the practical context that we've considered. Of course, there's others where this problem is relevant. So in game theory, stuff like this. But if you consider only these, I'd say, from my understanding, left tail actually trivializes the problem because negative values of beta means you're actually not excluding anyone anymore. And fat right tail means that you just decay faster, essentially, because you're excluding more and more. For a given sample n, you're actually excluding a larger fraction of your sample. So, I mean, I could be surprised because I was surprised with, for example, the uniform result. So I think the uniform is nice because it's the difference between having something unbounded and bounded. It seems like here it makes a big difference. So maybe something to explore would be maybe other strictly bounded continuous distributions, I'd say. For example, if you have I think a beta distribution or alpha. So many. Yes?
So one question about when you set the model, you said right away that for optimality you put the die like the 2-1.
Yeah.
And what's the physics related to this parameter? Does it change the sparsity or just does it redistribute the portfolio without changing it?
So basically what it gave was that, so you can rewrite the self-consistent equation. And something that's going to be important is the average of 1/z. Because, so basically, if you carry zi through, it gives you some beta j squared over zj, and then beta j over zj. So you can still do the same central limit stuff. It's just, the question is, what can go wrong is if this thing kind of diverges. Yeah. So it's the diagonal. So basically, if the diagonal is too close to 0, everything goes to,
Yeah, sure.
But other than that, it's kind of a rescaling in a sense of because of the, I mean, not exactly a rescaling, but you can still find the same self-consistent equation and then the statistics of Z. So actually, let me just correct this. This is if Z is independent of beta. If Z is dependent on beta, then I don't know, but then you'd actually have a new parameter, which is just beta j over Z, and it's a new random number. So it's the distribution of this. It's going to be important.
Okay.
But if it's something else independent, it appears not to change actually much.
So the sparsity is preserved.
Yeah. Yeah, because the sparsity is actually kind of the competition. So what I'd expect, once again, is in the same sense for the mu i's, if you have a horrible Z, well, you'll be excluded. So if they become related, your threshold is probably going to be on beta over Z, or beta as a function of Z, or something like this. Yeah. Okay,
Great. Perhaps we can check online. There are no further questions.
Yeah, perhaps I can ask one. Do you hear me? Yes?